Good evening and welcome to Monday Night Calculus. I'm here with Steve Kokoska and the legend Tom Dick. I'm super excited that you guys are here joining us this evening. Really happy to be providing this material with you, for you to be looking at and checking out. I would again just encourage you, if you have not yet, you can go to the Texas Instruments website and we'll post a link here in the chat momentarily. Look at this bulletin board post and find the materials for tonight's session, and be looking there for the coming materials for our next session. I believe that's November 30th, I think, is our upcoming session after this. So look for those problem sets and all of the previous problem sets there that you can use with your students. And I just want to say welcome to all of our students and teachers out there. If you guys are out there joining us live, we're super excited that you guys are here on a Monday night. Steve, I guess we can get started.
Okay, thank you very much, Curtis. It is a pleasure to be working with you and Allison, and of course, Tom, once again. I'm going to share my screen. I hope you can see that.
I can see it just great.
All right, we're going to go to full screen here, see if that works. How's that?
Looks perfect.
All right, very good. So tonight's topic is function analysis with graphical stems. And before I get to that, Curtis, I would be remiss if I didn't mention that there was some calculus in the national news here last week. This is not a political statement, but Joe Biden in his speech Thursday night mentioned the phrase inflection point at least twice. I'm not sure, maybe some of our participants know, I'm not sure if he took AP Calculus, and I'm not sure if he used it in the correct context, but it was nice to see him use an AP Calculus term. Kind of cool.
For sure.
And Mark Corrali sent us a couple of good questions, two good questions. I'm going to try to answer those, Mark, if you're out there. I'm going to try to answer those in the context of working through an example tonight. So tonight's topic is function analysis using graphical stems, and this has really been a bread and butter type problem in AP Calculus for decades. And there are lots of concepts here, and we could probably take 2 or 3 nights to talk about all the concepts. But what I'm going to try to do is to solve one kind of a long problem, and I'm going to discuss some of these concepts along the way. And I hope that I'll be able to answer some of your questions. I hope you'll have a couple for me. So here's the example that I'm going to work through. This is the graph of f prime. It's the derivative of a differentiable function f, and it's shown on this closed interval, -6 less than or equal to x less than or equal to 5. So although on the graph you don't quite see them, Tom is better at this than me. There probably ought to be some closed solid circles there to make that a little bit clearer. So the first typical sort of question here is, let's find the intervals on which f is increasing or decreasing. I'm going to scribble a little bit off to the side. Curtis, let me know if this is working okay. Most of us know that we have this theorem, and I'm going to try to be careful here with my implication arrow because I'm going to come back to this. And it says that if f prime of x is greater than 0, then that implies, on an interval, then that implies that f is increasing on that interval. And similarly, if f prime of x is less than 0, that on an interval, that implies that f is decreasing on that interval. Now, most of us remember that theorem, and most of us use this theorem in order to solve this problem. So I'm going to take a quick look up here at this graph and try to scribble a little bit on the graph. I see that f prime, let's see, is positive. Let's see, all the way from -5 here, all the way over to 1, and then it's positive again here from 3 all the way over to 5. So in my opinion, f is increasing from -5 to 1 and from 3 to 5. Now you'll notice that when I wrote those intervals, Curtis, I wrote them as closed, and I'm going to come back to that issue in just 1 second. And you'll also notice, let's see if I can scribble this in here, I also included x equal -3 in this interval. And if you look up here, f prime at -3 is 0, but I believe it should be included in that interval. So let's see, where is f decreasing? Well, I'm going to take a look at this graph up here. And where is f prime less than 0? Well, let's see, between -6 and -5. And I guess from 1 to 3. And again, I'm going to use closed intervals there. Now, I don't think this is a contradiction, for example, to have 1 in both places here. And the reason is because I do not believe that a function can be increasing or decreasing at a single point, a single value x. If you go back to, I think, the most common definition of increasing or decreasing, a function is defined to be increasing or decreasing over an interval, so that as we move left to right, for example, the function values are getting bigger. So as I think it's okay, according to that definition, to include a value like 1 in this example in both of these intervals. In addition, I think it's okay to include x equal -3 in here, because as we move left to right from -5 to 1, the function is increasing according to the definition. Now, another sort of subtle point here is, you'll notice over here on the right-hand side, these are implication arrows. They are not going in both directions. So it doesn't say that if f is increasing, then f prime of x must be greater than 0. That's not the implication. So going in this direction gives me most of the places, but I also have to consider these endpoints, or these places where the derivative is 0 or does not exist. So to sort of wrap up this part A, I think it's okay to include a value, those endpoints, in both intervals. I do not believe that that's a contradiction, and it's not a contradiction if you think about the precise definition of what it means for a function to be increasing or decreasing. Okay, let's take a look at part B. Now, what I've done is I've reproduced this graph here in all of these, and I'm sorry, there's a lot of words at the bottom here, but we won't have to go through all of these. This is another classic question on an AP exam. Let's find all the values of x in this open interval. I'm going to circle that for a second. If there are any at which f has a critical point, and let's classify each critical point as a relative minimum, relative maximum, or neither. So, okay, critical points are critical values. It's kind of odd. We say critical points, but we're really finding a value of x. We often think of points as a coordinates or an ordered pair. So I have to find all the places where f prime of x is equal to 0 or where f prime of x does not exist. So I'm going to find all the places where f prime is equal to 0 by looking up here at the graph. I have an x equal -5. I have an x equal -3. I have an x equal 1. And I have an x equal 3. So according to what this question is asking, I have to classify all 4 of those. I'll do 2 of them maybe and leave the rest for you. I have to find all the places where f prime of x does not exist. Well, this sounds sort of odd, and I think I've talked about this before on Monday Night Calculus. There are no places where f prime of x does not exist. Now, that's kind of odd looking at this because, well, I do see some sharp edges here, some corners, and some odd points over here, but those would be indications where the derivative of this function in the graph does not exist. So there might be some places where f double prime does not exist. But if you look at this graph, f prime is defined for all values in this open interval.
Hey, Steve.
Yes.
I do have a question that's already come in here. Alejandro, who's been a faithful attender, I recognize his name, asks if you're going to be talking about vertical tangents at all in this.
I don't think so. I don't think that comes up. Oh, there is one place where it does come up, so we might get to that. Yes, okay. There's one place here, I think, in a graph.
Yep.
If it doesn't satisfy his question, if it doesn't answer his question, have him ask it again, please.
Yep.
Okay.
Yep.
And we'll look at it.
And to that end, you're going to hit the points of inflections and cusps. It looks like
we're going to look at points of inflection for sure. Absolutely. Yeah. All right, so let's take a look at x equal -5. And I think this is a very reasonable type answer that we're looking for on the AP Calculus exam. At x equal minus 5, f has a relative minimum because f prime changes from negative to positive. It changes from negative to positive across that value x equal minus 5. You can almost feel the function decreasing and then increasing, and you feel that relative minimum. And at x equal minus 3, the function does not change sign, f prime does not change sign. So f has neither a relative minimum nor a relative maximum because, again, f prime does not change sign there. So we can kind of quickly look, I think, at what's going on at x equal 1. It has a relative maximum because you can see f is increasing and then decreasing. And at x equal 3, it has a relative minimum because it's decreasing and then increasing. So again, that's kind of a standard sort of a question on the AP exam. And I think that your students should be prepared to answer that sort of a question. Now, let me try to address at least one of the questions that Mark Corrali sent. You know, somebody asked, well, are there critical points at the endpoints of the domain? Well, I don't think that there's necessarily consistency here across all textbooks. And I think one way that the AP calculus program gets around this issue is this right here, is by asking you about an open interval. Find the critical values in that open interval, so we don't have to worry about the endpoints. And I think the way that a lot of textbooks get around this is that they simply define a critical value to be the interior of the domain of a function. Now, there are some other things to think about, and we can argue about this later on, but there are some other things to think about. Well, what if we look at a closed interval here, minus 6 to 5? One could argue perhaps that the derivative at minus 6, the derivative at 5 does not exist. On the other hand, one might argue that the one-sided derivatives are more appropriate at those endpoints, and those do exist. So no consistency here, and I think this is the way that the AP Calculus program gets around this, by looking at an open interval, by asking about an open interval. Let's take a look at part C. This one says, find the intervals on which f is concave up or concave down, and find the values, of x, at which the graph of f has inflection points. Well, before I answer this, I've got some answers down here, but let me scribble a little bit more over here. Here's the idea, the concept I think that most of us use. We know that f is concave up if f double prime of x is greater than 0. That's true. If that's true, then f prime of x is increasing. So I can look at this graph of f prime and I can identify where f prime is increasing, and that'll tell me where the graph of f is concave up. Similarly, if f double prime is less than 0, we know that the graph of f is concave down. We know that f prime of x is decreasing. And so I can use the graph here to answer this question. So, okay, I'm going to take a quick peek up here at this graph. I see that f prime is increasing minus 6 to minus 4. It's increasing again from minus 3 up here to minus 1, and again from 2 all the way over to 4. You'll notice here when I list concave up, I list these with open intervals. And I would argue a reason that I do that is because, again, I go back when all else fails. I go back to the definition. And again, there may not be consistency here, but I think perhaps a majority of textbooks define concavity at a single point, as opposed to increasing and decreasing. And concavity is defined in terms of a tangent line, and whether or not the function lies below or above that tangent line in a neighborhood. So because concavity is defined at a single point, I don't believe I can include those endpoints because, for example, there would be no concavity at one of those endpoints. Okay, it's concave down with a function where f prime is decreasing. Let's see, whoops, I'm sorry about that, Curtis.
It's okay.
Back up there. Is minus 4 to 3, it's decreasing. Minus 1 all the way over here to 2, it's decreasing. and 4 to 5, it's decreasing. So there I have the function f would be concave down. And my inflection points are where concavity changes. So given the graph, that would be where f prime changes from increasing to decreasing. Have I got all of these? -4, -3, yes, -1, 2, yes, and 4. I think I've got them all. How about that? So a couple of common errors here as we're looking ahead already to the AP Calculus exam. Given a question like this on the exam, a common error for students is to answer or to justify these intervals by talking about f double prime. You have to be careful in doing that unless you've made some sort of connection here, because the problem hasn't given you really any information about f double prime. It's given you a graph of f prime. And so the exam, we're really expecting justification in terms of the information given in terms of f prime. Another common error here is when students see this inflection points, not the x values, they're inclined to give us coordinate pairs here. And a common error is to look at the graph of f prime and give us something like -4, 1. Well, that's a coordinate, or that's an ordered pair on this graph, but it's not really right, because this is not certainly the value of f. We don't know what the value of f is at -4. So this is in a gray area. It depends upon who the chief reader is about whether or not this kind of a response would earn credit for the inflection point, or a value of x, or where the inflection point occurs. So as you're looking ahead, as you're preparing your students, that's a little bit to think about.
Hey, Steve.
Go ahead.
I think this is related to this, and I'm going to just bring it up real quick. One of our teachers here gave this set of questions today to his students, and found that one of the common errors that they made was talking about justifying relative extrema by just simply stating that f prime was equal to 0, and not talking about either side of that.
Yeah, and saying that f prime is equal to 0 is not justification for a relative extrema. That's identifying a critical point.
Right, right.
And so in order to justify that as a relative extrema, you have to talk about the sign of f prime on either side.
On either side.
So it's either a relative minimum, a relative maximum, or it could be neither. And that's
right.
just justified by, in this case, looking at the graph.
Perfect.
Yeah, good question. Good question. All right, here's part D. Says, for x in this open interval, once again, find the intervals on which f is increasing and concave down. So this is another common question. And for us tonight, really what we're going to do is just sort of combine a couple of answers that we have already. Let's see, we know that f is increasing on these intervals. That's from a previous question. That's where f prime is positive. -5, let's see, to 1, 3 to 5. Yes, I can see that by looking at the graph. Concave down, where f prime is decreasing. We just took a look at that. So there are those open intervals. And now all we really have to do is take a look at the intersection of these intervals, of these sets. And if I've done everything correctly, I've got -4 to -3, -1 to 1, I think that's right, and 4 to 5. Yep. So that would be where f prime is positive and f prime is decreasing. Beautiful. Nice question. Very common, very logical, and at least in my mind, for my students, very step-by-step procedural sort of a problem. Good.
Yeah, this is a good common question. I like this one. I like this a lot.
Very common. And this is a nice one too. It seems to me that I've seen a lot of these in recent years. And especially in 2020, we saw a lot of these types of existence questions. Must there exist a value of c in this open interval -4 to 4 so that f double prime of c is equal to 0, and justify your answer? Well, all right. It sort of makes sense here to take a look at f prime of -4 and f prime of 4. And if you take a look at the graph, I think that gives you the same value 1. So let me throw out one question here for the participants. So what theorem here am I thinking about? What do I want to use to sort of prove or disprove this? What theorem would I like to use in order to, let's say, prove this? I started by taking a look at f prime of -4, and I went up here to the graph and I got that value of 1. I took a look at f of 4. That value is 1 also. And so I want to know now, does this guarantee that there is a value of c in that interval so that f double prime of c is equal to 0? So what theorem am I going to use here in order to try to prove this?
So Steve, we got a little bit of a delay in here.
Okay, that's all right.
We'll have to watch for that. But
well, how about you, Curtis? Can you answer that? I don't want to put you on the spot.
Don't put me on the spot tonight.
Well, I'll give you a hint. All right. It has some nice initials here. We might use the mean value theorem here. And this is actually a special case of the mean value theorem. Do you remember this one, Curtis?
I don't. Well, and I'm not seeing what you've got. The mean value theorem is what I was thinking initially.
So the mean value theorem, actually, when we teach this, we often talk about the special case of the mean value theorem first, with the value here at the endpoints are the same, and that has a special name too. Anybody got that at all?
I got Rolle's theorem coming.
Oh, on the money. Beautiful. Beautiful. So that's Rolle's theorem. Beautiful. So I guess when I first started to solve this problem, Curtis, I took a look at f prime of -4 and f prime of 4, and I got the same value and said, you know, this is looking like a great Rolle's theorem problem. I looked up here at f prime and I said, you know what, it's continuous on -4 to 4. And before I get to the next step, I even cheated a little bit. I drew a line here, this sort of secant line between those 2 points.
Mm-hmm.
And I thought, well, you know, it sure looks like I might be able to find a place where the slope is the same as the secant line. This has got to be true. But be careful. F prime is not differentiable on this open interval. And how do you know that? We know that because we talked about this just a little while ago. There's a corner point there. There's a corner point there, sharp edge there. So we know from the graph that F prime is not differentiable. Now, there may be a value, and I think I even found one, where F double prime of C is equal to 0, but we are not guaranteed that there is one in this interval. So the correct, answer here is we are not guaranteed that there is a value C in this interval -4 to 4. That's a cool problem, especially because it's visual. I think students might jump to a conclusion here and say, oh, there's got to be one.
Right.
Nice
I certainly would have.
I don't believe that. All right. There's a part F and G in here, Curtis, that I'm not going to do, but I'm going to leave as open questions. I think these are good questions that teachers could do in their class tomorrow with their students. You know, here's the graph of F prime. Let's suppose that F of 0 is equal to 1. Can you give me a rough sketch of the graph of y equal f of x? That's a great one. And let's even go the other way. Can you get a rough sketch of the graph of f double prime? Jeepers, we've talked quite a bit about f double prime already. Can you get a rough sketch of it? I think both of those are excellent questions. Once you answer part F here, you should also ask your students to look at the relationship between these two graphs, f and f prime, and see if it makes sense. And even the relationship between this given graph, f prime and f double prime, and make sure that those relationships make sense. Great question, bringing into, I think, a lot of different calculus concepts.
Hey, Steve, I think we do have a request to see one of those two worked out. I'm not sure which one Debbie is looking for, but how to teach that. Okay.
How to teach
that.
Okay, so I'll just scribble a little bit. Tom, correct me if I make a mistake here, but here's the way that I think I would approach this one. I think what I would do is I would start by defining f of x to be f of 0 plus the integral from 0 to x of f prime of t dt. And I think we might talk about that, or we have talked about that as a net change theorem. This sort of an equation comes up all the time in AP calculus, comes up frequently in particle motion problems too. So the way that I would teach this is I would start by looking at this expression right here as part of my net change theorem, also coming also as a result of the fundamental theorem of calculus. And then I would start plugging in values and use some geometry. So I'll take a look at 1. So if I wanted to find f of 1, that would be f of 0, which we're told is 1, plus the integral from 0 to 1 of f prime of t dt. So to find this definite integral, I'm going to go up to the graph and I'm going to use geometry. The integral from 0 to 1 of f prime of t dt would be the area of this region right in here, which happens to be a triangle. So I can find the area of that triangle as 1/2 the base times the height, and I add that to 1, and now I've got a value of f of 1. And I would continue and find f of 2 and f of 3. I got to be a little careful as I work over here because I've got a circle. I've got to be a little careful as I get in between -1 and 4 because now I've got, well, what looks like a parabola. Now you can attack that in 2 different ways. One way I think that I would do it in class is just to approximate the area under that curve. I just do my best because I've got some nice delineated rectangles in there. Another way, a little bit more sophisticated way, is you might be able to look at that and figure out what the equation of that parabola is. And if you do that, you can actually find an antiderivative and find some areas exactly.
Right.
So that's a neat problem. I hope that helps
you
a
did
little.
a really nice job of giving us some good points there to find the equation of that parabola.
I hope that helps a little bit. All right, I'm going to shift a little, Curtis. Take a look at a couple of the solutions here. I want to leave a little time for Tom. Let me see if I can make this a little bit bigger here. I apologize. Let's see. Whoops, I'm sorry about that. Let's see. I'm going to try to make that, whoops, a little bit bigger.
That looks nice.
You can see that?
I can see it.
Yeah?
Mm-hmm.
All right. I know there's a way to make that a little bit bigger, and now I don't see it here. I'm sorry about that, Curtis.
That's okay. Maybe that magnifying glass.
Oh, there we go. Beautiful. Thank you very much. Okay. So on this problem, number 1 is very similar to the example that I just went over. And so I'm not going to go through this one in gory detail. And this one, we're going to classify all the critical points once again. So that's very similar to something that we did a minute ago. In part B, we're going to look for inflection points once again. We talked about that a little bit. In part C here, we're going to find the intervals and where f is decreasing and concave up. We talked about that sort of an idea. And here we're going to look at increasing and concave down. So we looked at all of those ideas, and Curtis, we're going to be posting these solutions so people can take a look at that. I'm going to take a quick look at 2 here. I thought this was a great question. 2 says, if it's known that f prime of 4 is equal to -6, find an equation of the tangent line to the graph of f at x equal 4. Well, we have a point given to us. We need an equation, we need a value for the slope. So we need to know what f prime of 4 is equal to. Now, I can't look at the graph. I'm sorry, Curtis, I'm not going to arrow back up to that graph, but I can't look at the graph and read off the slope because this is part of the graph that was part of a half circle. So in order to do this, I've got to come up with an equation for that half circle. I'm going to plug in f prime. I'm going to plug in 4 into that equation because remember the graph that was given was a graph of f prime. So I'm going to plug in a 4 here. There's a minus sign out in front. So son of a gun, the slope at 4 is -3. And there's an equation of the tangent line. That's a very nice question. Very reasonable, I think, AP type question.
Could I jump in here, Steve?
Please.
Yeah. So this is a very nice way of doing it with the you did it analytically by figuring out what the equation of the function had to be, at least over that part of the domain. It is possible that some people might have used a little bit of geometry here. It's not geometry I would assume all students would remember, but the tangent line to a circle is going to be perpendicular to the radius. And so if you drew a radial line from the center of that half circle out to that point, you could figure out the slope of that radial segment, take -1 over
that slope,
the slope, negative reciprocal, and that would give you that same answer that you got. I mean, you got
very cool.
Your answer's fine, but there is a way to use a little bit of geometry there.
I like that. I like that,
that,
Tom. I like that approach a lot. I think that's probably what would have been natural for me.
Okay, let's take a look at f double prime of 4. There may be a geometric way to do this one too, Tom. I'm not sure, but here's the way I did it. I took a look once again at this analytical expression for f prime, that half circle, that bottom half circle. I found the analytical or symbolic derivative of that, or f double prime, and I plugged in a 4 for a 4/3. Is there a way to do that geometrically, Tom?
You know, I'm just realizing I actually answered part B. I gave you the geometric way.
Yes, you did.
And it's really equivalent to what you did in part A, is that, you know, you can just figure that, oh, my, since the center of that circle is 0, 0, the sum of the squares of the coordinates has to be 25. And so that's kind of equivalent. Yeah, I'm sorry. I kind of jumped to part B here. So that's exactly what you did.
Yep.
That's the geometric way.
That's the geometric argument. Okay.
Yeah.
Very good. All right, I'm going to take a look at one more quick one, Curtis, because I really like this one, and then I'll pass it over to Tom. Let's let G be a function defined to be the second derivative of f, and let's see if we can sketch a graph of G over this open interval. I don't know if I've ever seen one like this on an AP Calculus exam. This would be a bear to grade, I'm sure, but this is kind of a cool problem. Can you actually sketch f double prime by looking at this graph of f prime? So if I've done everything correctly, Curtis, f prime is colored in blue and f double prime is colored in green. And you'll notice f double prime here over this interval is a straight horizontal line. Let's see, is that correct? Yes, because over that interval, you'll notice that f prime is a straight line with constant slope. So its derivative would be that slope, which I think is -2. There is no value here. I didn't put this in, but there is no derivative here. So there's a very small open circle there. There is no derivative here, and this might answer part of the question about a vertical tangent line. You'll notice that f prime here, as we get closer and closer, I think this is a -5 here, that the derivative gets closer and closer, or decreases without bound, gets closer and closer to -infinity. As we get closer to 0 here, the derivative of f prime is 0, and then as we approach 5 from the left, the derivative increases without bound to +infinity. And over here we have two other line segments, the derivative of f prime. That's a really nice problem. I don't really have too much time left here, but that's a good one to talk through with your students. And there's a couple of questions that I'd like to leave you with here. Number 4 says find a positive value a so that f prime of a equals f double prime of a, and then find f triple prime of a. I found a value, oops, sorry about that, Curtis. I found a value that works, I think here is 6. And I'll just add in here 2 questions, maybe for our participants to think about. How do I know that that's true, that 6 works? And how do I know that the third derivative at 6 is equal to 0? And then I'm asked, is there a negative value x so that f prime of x equals f double prime of x? And I think there is at least one. And I found one analytically. and we'll be posting these solutions. So that's, I think, a good problem too. All right, Tom, I'm going to pass it over to you if it's okay.
Okay, great.
All right, let's see. I'm going to try to stop sharing. There we go. How's that?
All right.
That's perfect.
I'll try to share my screen. I'll look to Curtis and Steve to give me some feedback if they're seeing my, I'll start out with the TI-Nspire screen. Is that showing up? Good.
That's showing up great.
Perfect.
Great. Okay. So I wanted to pick up right where Steve left off. And I wanted to add that very, very often this kind of question, I actually had a graduate student kind of looking at old AP exams, and there was a question similar to this. We think it's appeared almost every year for the last 20 years. Where you have some graphically presented function and you're asked to use calculus to interpret what's going on. And very often it's the function is presented as a collection of line segments and semicircles, sometimes parts of a parabola, and we've seen both tonight. And the intent of those questions really is for students to use what they know about calculus and some geometry. So for example, if this is the graph of a derivative, then the second derivative value of our original function would be the slope of this graph. And so where it's a line segment, that should be something we can use really our high school algebra knowledge to find the slope. But we need to know how to make that connection. So what I've done here is really recreate that same graph from the problem set. And this graph here is actually drawn, just made using line segments and parts of circles. But if I'm teaching this and I want to use an example like this is nice for kind of illustrating the problem. But if I do want to use the technology to, for example, as a kind of a check on how we're thinking about things, I really want to go ahead and analytically define this function. Now, Steve did that part way when he was looking at the semicircle part. He actually went ahead and found an analytic formula for that part of the graph. But I'm going to go to another page here where I've got that same graph. Now it's in blue, but this is actually not drawn with geometry tools. It's an actual analytic formula for that function. Okay. And so that takes some work. I'm just saying, I'm not, we actually see when we're grading AP exams, we will see that functions like this, some students go to the trouble of finding the full-fledged analytic form for that function. But that's really not the intent of that question. It really is to use your calculus knowledge and geometry to visually interpret what's going on. However, if I'm using a graph like this for a teaching tool, I might very well want to have an analytic form because that allows me to do some things using the technology to illustrate some key ideas. And so I just want to go ahead and take a look. Let's see what the formula for this function looks like. I'll go down to my graph entry edit. There's function. And let's go up and take a look. And there it is. That's that piecewise defined function. It had 5 different pieces. 4 of them are line segments. So you see 4 linear function formulas. And then that middle one is that bottom half of the circle of radius 5 centered at the origin. So this is just showing how that's formatted. It took a while to enter. But once you have that analytic form, it does allow you to do things such as define the derivative. And Steve wound up looking at the, I think his graphs were green and blue. He looked at a graph of the derivative of this, and he did a very nice analysis. And it's the kind of analysis you would do for AP exam in terms of interpreting visually what was going on with the original function to figure out what the graph would look like on the TI-Nspire. So let me go ahead and let's see. I think I've got this hidden. There it is. Okay, and things behaving a little sluggishly. Oops, wanted to see that again. All right, let me reveal that graph again. There we go. So there's that graph of the derivative. Mine's in red here. And it's very much like the graph that Steve showed. Might be interesting to see what does the technology do at these points where Steve actually drew in the open dots at the endpoints of these pieces, line segment, where the derivative of this blue function graph is undefined. Might be interesting to actually look at the trace and see how that behaves. So I'm doing a graph trace, and I'm on the blue function graph. Let me go ahead and up arrow to the red function graph. Okay, and there we have that derivative. So this would be our second derivative, since the blue function is actually the first derivative what we're looking at. There's 0 here, but I'm curious what might have happened, say at this sharp, it's kind of a hybrid between a corner and a cusp, right here. What does the trace say at, say, -5? So I'm going to enter in -5 and jump over there. Notice it's showing this, that dotted line is really representing that it's undefined. Oh, and it's even reading out here down here that's undefined. So that's kind of nice. So it's picked up that the derivative does not exist at that point, the derivative of the blue function. Okay. All right, I'm going to switch gears here a bit and switch platforms. Because I think sometimes people look at the TI-Nspire is an incredibly powerful machine, but lots and lots of folks use TI-84. And TI-84 is a really nice machine too. It doesn't have computer algebra, but it's very powerful. Certainly can do a lot of calculus with it.
Tom, as you're switching over to the 84, we don't see that screen yet, by the way, but as you're switching over to that, you don't have to do this, but another thing I think you can do on this screen is you could actually define F on the screen the way that I did on a piece of paper with a piece of paper and a pencil, right? You could define F of X to be 1 plus a definite integral from 1 to X of F of t dt or F prime of t dt. And so you could actually put all 3 of those graphs on the screen, I think. You could put F, F prime, and F double prime. And if you hid all of those definitions, there's a great exercise for students to identify F, F prime, and F double prime. That's
right. Yeah.
Right?
Show them all 3 and say which one is
which. Is which, yeah. That's a great question.
Very nice.
Yeah.
That would be a fantastic
I like that
exercise. And Tom, while you're also switching over, I've got a couple of things to go through from the chat. So you go ahead and switch over to the 84. But I had a question come in about whether we will continue these chats and these Monday Night Calculus series. And we absolutely plan to continue these into or at the end of November and then into the spring. We will kind of restart in the spring and have some more after we take a December hiatus. And we will rejoin that in the spring. So looking forward to doing that as well. And Tom, there's someone on here that's a big fan of yours from the 1985 UNH softball team.
Oh my
You got
gosh.
a nice comment there. We'll have to
Oh,
look
you
through there
wouldn't
later.
believe what the name of our team was. Koshi's Dogs.
Say that again.
The name of our team was Koshi's Dogs.
The Koshi's Dogs. All right.
That's because they leave a residue around every pole. So,
Okay.
I'll get you back on track here.
All right. Yeah, okay. Rescue me here. So Curtis and Steve, maybe give me some feedback. Are we looking at my 84 screen now?
We are
Yes,
indeed.
sir.
Fabulous. Okay. I'm going to go to the Y equals menu. And boy, you can't see the whole thing, but you can see on Y2, I actually have that same 5-part piecewise defined formula there. And so you definitely can do those on the 84 also. We'll take a closer look at that, but I thought I would leave my Y1 blank here just to kind of illustrate how you do a piecewise function. Okay, so we'll do a simpler one just for illustration purposes. If you go to your math menu on the 84 and you scroll down all the way past, well, there's a numerical derivative. We're going to make use of that here in just a little bit. Definite, summation, log base. There's what we're looking for. It's that piecewise. I'll hit enter, and I get a little kind of dialog box here and ask me how many pieces do I want to have for my function. I'm going to go ahead and just go with 2 pieces. So I hit the left arrow, go down to 2, and then we'll enter OK. And it sets up a nice little template for me where I can put the formula for each piece as well as the part of the domain for which that formula will be valid. Okay. So I'm going to put in a formula. Let's see, let's put in the opposite of x. And then for the domain of that part, let's do, we'll go to the test menu. And
recall under those conditions there, you've got some predefined pieces.
So I'll do number 1 there. That looks good. X less than or equal to 0. So we'll use negative x for x less than or equal to 0. And then for the second formula, I'm going to actually put in x squared for x greater than 0. And then again, I'll go to the test menu, conditions. Oh, I think I have a redundant x here, probably. Yep. So my bad. Should have let it do more work for me. Okay. So x greater than 0. And so this is a 2-part or 2-piece piecewise defined function. And so I don't get too much on the screen, let me turn off Y2 momentarily and I'll graph that. And there we go. And notice that it's negative x for x less than or equal to 0, x squared for x greater than 0. And you can do up to, on the 84, you can do up to 5 pieces on a piecewise defined function. If there's more than that, you'd have to figure out, you might have to actually plot it as 2 different functions, like part of it in Y1, part of it in Y2, and look at it that way. But in this particular case, let me go ahead and clear out Y1. Y2, I went ahead of time and put in that same formula. So this is our first linear piece, second linear piece. There's that bottom half of the semicircle, the bottom half of the circle, 2 more linear pieces. And that's our Y2. I don't think that window I had is going to be big enough. So let me go to the window. I think I want it to be twice as big in both the X and Y direction. Just want to show you that, let's see, this X min, I could figure out what that is, but I could just multiply by 2. And it does that quick calculation for me. So if I just want to double the size of the window, I'll just do that now for y min and y max. Multiply by 2.
So naively, Tom, one might be wondering why you would want to double both of those.
Well, it was because knowing that picture that you had, I noticed it was from -12 to 12 was your domain. And I think it was like -8 to 8 was the kind of the Y range on the graph that was given to us. So when I looked at this window, I said, oh, I need to approximately double both to do that. But so it was really knowing what the picture needed to look like.
Okay.
And I think we are ready to graph. Ah, there we go. There's that picture again. So that's our function that we were presented with. And on the 84, just like on the Nspire, it's going to be a numerical derivative. It's not going to be a computer algebra derivative if you have a CAS machine. But we can go back to our y equals menu. And I'm just going to go down to y3. And I certainly don't want to re-enter that whole y2 here, but I can now just go to the math menu, scroll down to the numerical derivative. We'll take a derivative with respect to x, and now we want to just put in y2.
Tom, I'm really glad you're showing the power of 84 here. One thing that while you're entering this in, I was noting you can do those piecewise defined functions. You could actually do that on the home screen where you can see all 5 pieces if you wanted to do a larger one like that, like you're doing now.
Right.
That one, you could do it there. And I also noted that this particular one has a nice advantage because you do have those 2 linear pieces, which could have been made into an absolute value if you wanted to.
Exactly. That's the kind of cleverness you might need to show if you, for example, had a 6 or 7 piece function. I think, Steve, you and I did a presentation once where we had something that had 6 pieces to it.
Yeah.
And we needed to pull off that kind of stuff. So.
Yep.
All right, well, drum roll here. Let's see if we see a derivative of our y2 come up.
Tom, before you do that, can I ask a question about this page?
Sure.
So as you look at y3, I don't expect an answer here. Curtis might be able to answer this one, but you know, this bothers some of us as we look at right after or right to the right of the vertical bar where it says x equal x.
Yes.
You know, this variable x being used in a couple of different ways in this same expression. And, you know, we as mathematicians probably wouldn't write anything like that on a piece of paper with a pencil. And we'd hope that our students wouldn't write anything like that on, you know, the AP calculus exam. Yet that's the calculator syntax, right? I mean, is there a way around that? I don't know. I mean, that's sort of a rhetorical question. I don't think there is.
Well, I'd have to check into it. I'd be a little leery about maybe changing the variable, but
yeah,
you do bring up an important point. If this had said x equal 3,
yeah,
then it would have done the numerical derivative of this piecewise defined function at that one point.
Right.
It would give me, you know, its best value.
Yep.
The x equal x, these 2 x's, this second x is actually the x coordinate of the pixels as you move across the screen.
Yeah.
So this value of x will change as you graph.
Yep.
And so it's going to do that numerical derivative for each and every value of a pixel as we march across the screen.
Yeah, that's a great
I do agree with you. It looks locally here, it's kind of weird. Yeah. It is interesting that this numerical derivative, you know, it's the more recent versions of the 84 now have this nicer kind of syntax and the two-dimensional. It looks more like a derivative. We don't have that n-deriv notation.
Yeah, the math print is a really nice update on there.
It is. Yeah, it really helps you do a check on whether what you've entered is what you intended.
Steve,
I
don't
take a look at the graph.
I don't think there is a way around that x equals.
Yeah, I didn't think so.
I was just trying to store a function in terms of some other variable beside x, and you get some error error notifications, and so I think you're limited to that.
Okay.
You just have to kind of think through.
Yep, it's calculator syntax, and you have to be able to work with it. Yep. Yep.
So here we go. It's really a very nice graph. I think very accurate for what
Indeed
we had before. But you know, I don't know if people notice, but I saw a little thing here. I don't know if you see my arrow. I'm kind of circling this point here. It looks like it plotted a point here, right?
What is that, Tom?
Well, I think it actually came up with a numerical derivative at that corner point where we know the derivative of this red function graph would not exist at that sharp corner. But because it's a numerical derivative, it's actually just using a difference quotient with a very small interval. And so it's actually coming up with a value. So if we turned on trace here and we jumped over to, let's see, what is that value? Is that 7? 1, 2, 3, 4, 5, 6, 7. Let's jump over to 7. Oh, I'm on the red function graph.
Yes.
Let me go ahead and arrow down to the black function graph. Ah, you see this?
Yeah.
That's a bogus. We know from calculus that's a bogus value, but it's not that the calculator has made an error. What we need to recognize is it's not doing a true derivative. It's doing an approximation. And so it's giving us an approximation that we don't want to use as an actual value there because of that sharp corner.
And that's an important learning thing. And as Tammy Jones points out here, you know, understanding the process on using your TI-84 or some other numerical calculator as opposed to a CAS machine where it has the ability to do some of these computations analytically, that we're using a numerical approximation for this derivative, you know, is an important thing to point out and to learn a little bit about the way that it does the numerical approximation and what are some of the things that can come up as a result of doing that.
Just for grins, I'm going to jump over to -5 because that's where we've got actually a vertical asymptote for our derivative, right? It's definitely not defined. Notice that. It's still coming up with about, because what it's done is calculate a difference quotient using two function values close to -5. Comes up with a number, but it's not one we would want to use. Okay. Pretty much anywhere else, if you avoid those points of non-differentiability, we're going to get some pretty good values. Yeah. All right, that's about all I've got.
That's a really good.
Close to out of time.
That's perfect, and that's a really good way to kind of wrap things up and thinking about investigating the tool you're using and knowing things that you know from looking at the graph. If I can look at this graph and have a conversation with my students about what I'm seeing and what I should expect to have in terms of the values I'm going to return, and trusting my gut in terms of knowing what I should be seeing, and then getting that quick sketch from the calculator on some of the other pieces and being able to do that. That's really, really good. Well, Tom and Steve, this was yet again, a great success this evening. I really enjoyed the session this evening. Steve, you put me on the spot again, and now I promise I promise I'm going to work these problems ahead of time for the next one. So I'll be prepared to answer those questions on the spot. Normally I've got pretty good calculus intuition, but occasionally I forget the names of theorems. And that's just bound to happen. So, but I just want to again encourage everyone to be sharing these with your students and getting your students involved in attending on these evenings. We have the chat here going, and certainly I will stop the conversation and insert those questions as your kids ask them. So we'd love to have your students join. And if there are some students out there, thank you for taking your Monday night and joining us. We will see you guys in a few weeks. We've got another Monday Night Calculus, the last one of our fall sequence is coming up on November 30th. So we'll be looking for you on November 30th right here on our YouTube channel. Check out the posting for that coming up. And then we will make an update to that bulletin board blog post with our schedule for the spring and the topics and things that we'll be covering in the spring. We'll be doing that in the coming weeks, preparing for our spring sequence. So enjoyed this evening, and I hope to see you guys again soon. Good night.